Hi guys, how are you doing? Today I'm going to solve problem 11 of the book of Halliday, the volume 3. It's the edition 10. It's a problem about the law of Faraday, or the law of induction. It's about a coil that is inserted in a magnetic field point into the page or into the video. If you're watching, you're probably watching a video, and what we have to show is we have to demonstrate the form of the electromotive force. So the book, the problem gives us the expression for the electromotive force, and the letter B, this is the letter A. In the letter B, the problem asks you to determine the value of the product of the coil, because there are any coils here where I am drawing, even if it's not clear, but you have to look at the problem like this. So there are any coils, and this is the dimension of these rectangular coils. They are all the same dimension. They all have the same dimensions. So the problem, let's first do letter E, and let's do that fast. So in order to calculate the electromotive force, or the expression for that potential, because it is kind of a potential, the only thing you have to do is calculate the magnetic flux across all of the coils. So you have a flux, obviously you have a magnetic flux across the coils, which is by the definition of a flux equals the integral of B scalar product the element of area. But as you know, you can take the vector B, because it is a constant, out of the integral sign, so equals B, and this is a scalar product, so you have a cosine factor here, cosine, and actually there is an n factor here because you have n coils. So this is the total flux across all of the coils. So the only thing you have to do now is to derive this relative to the time, because that's the definition, actually. Maybe not a definition exactly, but that's, you can call that the definition of the electromotive force. So the only thing you have to do is derive. You have minus here, derive the cosine of theta relative to the time, and as you know, it's minus sine of that angle times the derivative of that angle relative to the time. So you get this expression for the electromotive force. The factor n, B, the area, as you know, is obviously A times B, the sine of theta, this derivative, and you have to note that this derivative is actually the angular velocity or angular frequency, as you may like to call it, because it is how the angle varies with time, and since it's a constant thing. You don't have, for example, acceleration, angular acceleration. You may notice that this thing equals the angle of revolution divided by the time needed to make that revolution. So 2 pi divided by t, and 1 divided by t, or the inverse of the period, equals the frequency. So you have to P in this frequency here. With that expression, you actually can get an expression for the angle theta, because you have the theta equals 2 pi, the frequency, this letter is not nice, 2 pi the frequency times the frequency dt, and you do a simple integration, you get this thing. Of course, use the initial condition, the angle at the initial time is 0. So you have the final expression is relatively simple. You have 2 pi times the frequency times the sine of 2 pi frequency and the time. So that's the form of the electromotive force. So I'm going now to letter B, where we have to calculate some factor. I will stop right here and go back to letter B. So now come back. I have written down this expression like the book did. I have this this number here, which is the amplitude of the electromotive force, the magnitude of the electromotive force, and it is equal, as you may already notice, equals N B. This is a B, A, AB, letter cases, and you have 2 pi and the frequency. So and the letter B is very easy. The problem gives you the magnitude of the electromotive force, the frequency of the rotation of the coils anyway, and the magnitude of the magnetic field. So the only thing you have to do is to make a substitution. This may sound ridiculous, but that's the only thing you have to do. So you have to determine this factor, which equals this divided by 2 pi fb. And actually I'm not going to calculate this in here, because the purpose here is not to calculate things. It's just to show what's the right direction you could take on to handle the problem. So this is 2 pi 60 second minus 1, and you have to notice that second minus 1 equals hertz. This is the same unit. And the magnetic field, this is in Tesla, and you may notice that the quantity here, you have to obtain a quantity that's meter square. So because this is length and this is also length, and this is not, this is dimensionless. So the only thing you have to do now is take a calculator, or waste a lot of time of your brain to make this calculation and get the answer. But that's not, I think that's not the important part. So the final answer equals 0 times 7, if I'm not wrong. This is 9, here is 9, and here is 7. I hope I didn't make any mistake. So this is the final answer. And this is kind of important question, like from the point of view of a basic experiment, because if you have coils, you can ask yourself how many coils and what are the dimensions of my coils that I needed to have in order to obtain certain current or some voltage things like that. So I hope you have enjoyed the video. I hope it helped you, and I'll see you again in the next one. Bye bye.